NENOMATICA, where mathematics meets YouTube excellence. Welcome to today's lesson on algebraic factoring. Factoring is a fundamental concept in algebra where we break down an expression, such as a number or polynomial, into a product of other expressions which, when multiplied together, give the original expression. Let's start with a familiar concept, factoring numbers. We usually do this with numbers all the time. For example, the number 12 can be factored in several ways. 12 equals 2 times 6 or 3 times 4 or 2 times 2 times 3. One common approach to factoring numbers is to express them as a product of prime factors. For 12, this would be 2 squared times 3. When we factorize a number, we're essentially breaking it down into its building blocks. Let's look at some other ways to factorize the number 12. We can express 12 as 2 times 6 or as 3 times 4 or as 2 times 2 times 3. We can also use negative numbers, such as negative 2 times negative 6 equals 12, or negative 3 times negative 4 equals 12. We can even use fractions, like 1/2 times 24 equals 12. One common method for factoring numbers is to express them as a product of prime numbers. A prime number is a natural number greater than one that cannot be formed by multiplying two smaller natural numbers. So, for example, 2, 3, 5, 7, 11, and so on are prime numbers. Let's look at the prime factorization of 12. We can start by dividing by the smallest prime, 2. 12 divided by 2 equals 6. Then we divide 6 by 2 again, getting 3. Since 3 is already prime, we're done. So the prime factorization of 12 is 2 times 2 times 3, or 2 squared times 3. Another way to visualize prime factorization is using a factor tree. We start with our number 12 at the top. Then we choose any pair of factors, for instance 3 and 4. 4 can be further factored into 2 times 2. Since 3 and 2 are both prime, we can't factor them further. So reading the bottom row of our tree, we get the prime factorization. 3 times 2 times 2, or 3 times 2 squared. Let's try another example. Let's factorize the number 48. We'll start by dividing by the smallest prime number, 2. 48 divided by 2 equals 24. 24 divided by 2 equals 12. 12 divided by 2 equals 6. 6 divided by 2 equals 3. Since 3 is prime, we're done. So the prime factorization of 48 is 2 times 2 times 2 times 2 times 3, or 2 to the power of 4 times 3. Welcome to this video on factoring algebraic expressions. In this lesson, we'll learn how to take an algebraic expression and break it down into its fundamental factors. Let's start by understanding what an algebraic expression is. An algebraic expression is a mathematical phrase that can contain numbers, variables, and mathematical operations like addition, subtraction, multiplication, and division. When we have an algebraic expression and we want to factor it, we're trying to rewrite it as a product of simpler expressions. In other words, we want to express it as a multiplication of factors that cannot be broken down further. Let's look at a concrete example to better understand this concept. Here we have x squared plus 4x plus 3. This can be factored as x plus 3 times x plus 1. We can verify this factorization by multiplying these factors together. Let's expand x plus 3 times x plus 1 using the distributive property. First, we multiply x by x to get x squared. Then we multiply x by 1 to get x. Next, we multiply 3 by x to get 3x, and finally, we multiply 3 by 1 to get 3. Combining like terms, we get x squared plus 4x plus 3, which matches our original expression. Now that we understand the basic concept of factoring, let's look at some common factoring patterns. These patterns appear frequently in algebraic expressions, and knowing them can make factoring much easier. Let's start with the difference of squares pattern. A squared minus b squared can be factored as a plus b times a minus b. For example, x squared minus 9 can be written as x squared minus 3 squared, which factors to x plus 3 times x minus 3. Next, let's look at perfect square trinomials. A squared plus 2ab plus b squared is equivalent to a plus b squared. For example, x squared plus 6x plus 9 can be rewritten as x squared plus 2 times x times 3 plus 3 squared, which equals x plus 3 squared. Similarly, a squared minus 2ab plus b squared is equal to a minus b squared. For example, x squared minus 10x plus 25 equals x minus 5 squared. Let's also look at the sum and difference of cubes. A cubed plus b cubed can be factored as a plus b times a squared minus ab plus b squared. For example, x cubed plus 8 can be written as x cubed plus 2 cubed, which factors to x plus 2 times x squared minus 2x plus 4. And for the difference of cubes, a cubed minus b cubed can be factored as a minus b times a squared plus ab plus b squared. For example, x cubed minus 27 can be written as x cubed minus 3 cubed, which factors to x minus 3 times x squared plus 3x plus 9. Now, let's look at factoring general trinomials of the form ax squared plus bx plus c. Let's work through an example to understand the process. Let's factor x squared plus 5x plus 6. First, we need to find two numbers that multiply to give 6 and add up to 5. The factors of 6 are 1 and 6, or 2 and 3. Since 2 plus 3 equals 5, we'll use these numbers. So, x squared plus 5x plus 6 can be rewritten as x squared plus 2x plus 3x plus 6. Then we can group the terms x squared plus 2x and 3x plus 6. Factoring out the common terms, we get x times x plus 2 plus 3 times x plus 2. Now we can factor out the common factor x plus 2 to get x plus 2 times x plus 3, which is our answer. Let's try another example. Factor 2x squared minus 7x minus 15. Since the coefficient of x squared is not 1, we need to consider the product of a and c, which is 2 times negative 15 or negative 30. Today, we'll be learning about factoring algebraic expressions. Let's start with an example. Can we express 9x squared minus 16 y squared as a product of algebraic expressions with the correct coefficients? First, let's identify what type of expression this is. This is a difference of squares pattern, but with a twist. It's not just x squared minus y squared. Instead, we have 9x squared minus 16y squared. Notice that 9 is 3 squared and 16 is 4 squared. So we can rewrite this as 3x squared minus 4y squared. Now, we can apply the difference of squares formula. Remember, the difference of squares formula states that a squared minus b squared equals a plus b times a minus b. In our case, a is 3x and b is 4y. So, 9x squared minus 16, y squared equals 3x plus 4, y times 3x minus 4y. Let's verify this factorization by multiplying it out. We multiply 3x plus 4y times 3x minus 4y using the FOIL method. First, outer, inner, last. First, 3x times 3x gives us 9x squared. Outer, 3x times negative 4y gives us negative 12xy. Inner, for y times 3x gives us 12xy. Last, 4y times negative 4, y gives us negative 16y squared. Now, combining like terms, we get 9x squared plus negative 12x, y plus 12x, y minus 16y squared, which simplifies to 9x squared minus 16y squared. Let's look at our second example. Can we express 3x plus 2y as a product of algebraic expressions? To determine if this can be factored, we need to check if it can be written as a product of two or more algebraic expressions. 3x plus 2y is already in its simplest form. It does not fit any of our factoring patterns like difference of squares, perfect square trinomials, or a common factor. Therefore, 3x plus 2y cannot be expressed as a product of algebraic expressions with correct coefficients. It is what we call a prime polynomial. It cannot be factored further. Let's look at some other examples of expressions that cannot be factored. For instance, x squared plus 1 and x plus y plus z are prime polynomials that cannot be factored over the real numbers. Let's summarize what we've learned today about factoring algebraic expressions. We learned how to identify and factor the difference of squares pattern, even when the coefficients are not just 1. We also learned that not all expressions can be factored. Some expressions like 3x plus 2y are already in their simplest form. Remember, when factoring, always check for these patterns: common factors, difference of squares, perfect square trinomials, sum or difference of cubes. Practice is key to mastering factoring. Try factoring various expressions to build your skills. Next, you might want to learn about factoring higher degree polynomials or solving quadratic equations by factoring. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.